Our final lesson in Topic 1B is arithmetic sequences and series. In the first part of this lesson, we'll define an arithmetic sequence and we'll write the formula to generate the pattern of an arithmetic sequence, both recursively and with the explicit formula. An arithmetic sequence is going to be just a pattern of numbers. And in that pattern of numbers, the rule is you're either going to add or subtract as the pattern. So you're just adding or subtracting to generate the numbers in that sequence. Not every sequence of numbers has a pattern, but if you're adding or subtracting, the pattern is arithmetic. The common difference is what you're adding and subtracting. So that's just the number that you are adding or subtracting. So let's take a look at the pattern on the right. Is the sequence arithmetic? Well, let's take a look. From 3 to 8 to 13 to 18 to 23. And then the dots mean that the pattern would continue. Well, from 3 to 8, we add 5. From 8 to 13, we also add 5. From 13 to 18, I think we're recognizing that there is a pattern in this. We're adding 5 each time. So is the sequence arithmetic? We would say yes. What is the common difference? The common difference is positive 5. So you add 5 each time. What is the next term in that sequence? If we take the last term written and add 5 to it, we would get 28. That would be the next term in that sequence. To define a rule for all the terms in a sequence, we can use a recursive definition or an explicit definition. A recursive definition looks like a piecewise defined function. You'll have different rules for your input to get different values for your output. So it looks like a piecewise function. And what you'll do is you'll separate your formula. Instead of f of x equals, we now define it as a sub n equals. And n meaning any term in your sequence, a sub n would be the number of that term. Now you define it in two parts. We always have to define what the first term is, and that's when n equals 1. That would make sense. For anything greater than 1, we take the term that's before it and we add the common difference. I know this is a lot to write down, so see if you can get all of that to fit on that left-hand side. So again, the template is we define the first term. That should always be given to you in the information. And then D is going to be what that common difference is. All right, so let's take a look and see if we can define that recursive formula for the pattern up above. So we need to know the first term, a sub 1. What is the first term in that sequence? It's 3. We also need to know the common difference. What's the pattern rule each time? Well, we said each time we were adding 5, so the common difference is 5. That's really all you need to write a piecewise function. To write it as that, or to write a recursive definition, as your piecewise format, we'd say a sub n equals. That's going to always be our template on the left-hand side. On the right, we define a sub 1. Remember we said it was 3, and that's the rule when n equals 1. Now to get anything else, here's where we have to be particular to this detail. This term right here, if you see something that looks like a sub n minus 1, that means the previous term. And that is going to tell us how we get the next term. Recognizing up above, we simply said we're going to add 5 each time from the last term to get the next term. That's kind of what this template means. That a sub n minus 1 is just part of the formula, and we actually don't plug anything in for it when we write the piecewise function. But if we were to list out a bunch of terms, then we would. But then it says plus d, and we said d is 5, so that means from that term, we're going to add 5. And that's the rule for anything greater than 1. A sub n minus 1 means we take the last term or the previous term, plus d, so if we add 5 to the previous term, we would get the next term. That's a lot to take in, so make sure you can read through that and kind of process what I just said. Our next way to describe a function, hopefully would make as much sense, if not more, is an explicit definition. And the explicit definition also needs a sub 1, and we need d, and we use the letter n. So we use all three of those same variables, but now it's not piecewise. Now it's just a formula that will look kind of like slope-intercept form. We follow the model a sub n equals a sub 1 plus d times n minus 1. We plug in everything we know, which is the a and the d, and then we simplify. So now it says write that recursive formula as an explicit definition. So now we're going to use this model, and it'll give you the same pattern rule, just looking like a different format. Again, we need to know a sub 1, and that was 3. We need to know d, and that was 5. But now those are the only two things we're going to plug into our equation. N means any term in that sequence, and we don't know what n is yet, so we leave n for now. We'll write a sub n equals a sub 1, which is 3, and d, which is 5, times n minus 1. Now, order of operations would state to distribute the 5 in, and then we'll simplify. A sub n equals 3 plus 5n minus 5. Combine like terms here and here, and we would have a sub n equals 5n minus 2. This is known as the explicit definition. Let's put that to the test. I want you to figure out what we would call a sub 1. That means I'm going to plug in 1 on the left and 1 on the right and see if I get a match. If I plugged in 1 on the left, on the right I would have 5 times 1 minus 2. And that would be 5 minus 2, which is 3. And that was the first term. Let's try one more. Let's try a sub 2 and see what happens. If I plug in 2 on the left, we have to plug in 2 on the right. 5 times 2 is 10, minus 2, and 8 is the second term. This explicit definition can give you any term within your sequence. In our next example, we're given the explicit definition and asked to convert it to a recursive definition for an arithmetic sequence. Now remember, if you look on the left-hand side, for a recursive definition, we need a sub 1 and we need d, just like we did for explicit. Can you look at this equation and determine what those values are? Using the definition, a sub 1 is always going to be that first term in the formula. So a sub 1 should be 16. And then technically it's plus d times n minus 1. So this would be your d value, but it's negative. That would mean in your pattern you're subtracting 3 each time. To write this out then as a recursive definition, those are the only two parts you need, remember. We write out a sub n equals, and then we make that piecewise function. A sub 1 is 16, and that's when n equals 1. But for any term after that, when n is greater than 1, remember we take that a sub n minus 1, and we just leave it as is, and then we plug in what d equals in its place, minus 3. So to take the next term in the sequence, we'd subtract 3, and that would be our answer. And we would keep going with that pattern. And that's for values greater than 1. Now let's use what we know about the explicit definition with a little application. A high school auditorium has 18 seats in the first row and 26 seats in the fifth row. The number of seats in each row forms an arithmetic sequence. What is the explicit definition for the sequence? And then how many seats would be in the 12th row? Well, using what we know, the first term in the sequence is 18, a sub 1. But it doesn't say how much it increases in each row. We just know that by the time you get to the fifth row, there are 26 seats. If we take a look at our formula, the explicit definition, a sub n equals a sub 1 plus d times n minus 1, we can kind of work backwards. We know a sub 1, it's 18, so we'll plug that in. We also know that if n is 5, that's the fifth term, that our output is 26, and that would be what the left-hand side would equal. Substituting all that information in, now the only variable left is d, which is our common difference. To determine that value, let's just simplify this equation. We have 26 equals 18 plus d times, well, 5 minus 1, that's a d, sorry. Oh golly, 5 minus 1 is just 4. So I'm going to subtract 18 to move that to the other side. And we get 26 minus 18, which is 8, equals 4 times d. To get d by itself, divide both sides by 4. That means the common difference is 2. Each row of chairs in the auditorium has 2 more than the row before it. So then to write our formula, that would be a sub n equals 18 plus 2, which is our d, times n minus 1. And now just clean that up so that it kind of looks like slope-intercept form. Distribute the 2 in. And then combine like terms. 18 minus 2 would be 16. So 2n plus 16 is the explicit definition. And now it wants to know how many seats would be in the 12th row. Whoops, I don't know where that highlight thing came from. There we go, 12th row. What that means is that n equals 12. We'd be in the 12th row in that auditorium. Well, just 12, we don't have to have the 12th. In the 12th row, n would equal 12. So then we would write a sub 12, because we want to know how many seats there are in that row. 2 times 12 plus 16. Well, 2 times 12 is 24, and 24 plus 16, there are 40 seats in that row. Tomorrow we'll do a little bit of kind of connection with this material before we finish the lesson.